Hey there. If you've ever found yourself staring at a really complex fraction, wondering how on earth you're supposed to break it down, well, you've come to the right place. Today, we are absolutely going to level up your pre-calculus skills. We're tackling the advanced cases of partial fraction decomposition. So let's just dive right in. So you've probably already got the basics down, right? You know how to split up fractions when the denominator has nice, simple, distinct factors. But today, we're moving into the big leagues. We're going to master the techniques for the tricky stuff, denominators with repeated factors, and those stubborn quadratic factors that you just can't break down any further. Here's our game plan. First, we'll add a couple of new rules to your math toolkit. Then we'll see them in action with some examples. After that, and this is super important, we'll go over the common mistakes so you can avoid them. And finally, we'll look at why this is such a critical skill, especially for engineers. Okay, let's get started by officially upgrading that toolkit of yours. I want you to think of what we're about to cover not just as new rules, but as really powerful new instruments that are going to let you solve much more complex problems, especially as you start heading into calculus. So what are these powerful new tools? Well, it really all comes down to two advanced rules that unlock everything else. One is for repeated linear factors, and the other is for what we call irreducible quadratics. Let's break them down one by one. First up, repeated linear factors. Now, when you see a factor like x minus a that's raised to a power, let's call it n, you can't just create one fraction for it. The absolute key here is that you have to create a separate fraction for every single power, starting from 1 and going all the way up to n. If you skip one, the whole thing falls apart. And for rule number 2, what happens when you have a quadratic in the denominator that you just can't factor, something like x squared plus 1? Well, for these guys, the numerator can't just be a simple constant. It has to be a linear expression, something in the form of ax plus b. The big idea is that the numerator is always 1 degree less than the denominator. All right, we've got the rules, enough theory. Let's see how they actually work in practice. We're going to walk through 3 examples. And we'll start with a more basic case and then build our way up to a more complex problem. For our first example, let's take a look at x plus 3 divided by x minus 1 squared. See that denominator? That x minus 1 factor is repeated. It's squared. This is the perfect job for our first new rule. Okay, so following our rule, we set up our form. We need one term for x minus 1 and another for x minus 1 squared. Now, after we clear that denominator, we get to the really clever part. By strategically plugging in x equals 1, that whole a term just vanishes, which lets us solve for b instantly. We find out b is 4. Then, to find a, we just compare the x coefficients on both sides of the equation, which tells us a has to be 1. And just like that, we've got our answer. That original fraction breaks down beautifully into 1 over x minus 1 plus 4 over x minus 1 squared. See? That first rule makes it totally manageable. Let's kick it up a notch with our next example. Here we've got a mix, a linear factor, x plus 1, and one of those irreducible quadratics, x squared plus 1. This problem is going to need both our old skills and our shiny new rule number 2. You know, the setup here is absolutely critical. The linear factor gets a simple a on top, but that quadratic, x squared plus 1, it gets the full linear term, bx plus c. After we clear the denominator, we can use that strategic value trick again. Setting x to -1 gets us a equals 2 right away, but for b and c, we need to compare coefficients. We look at the x squared terms and the constant terms on both sides, and that quickly reveals that b equals 0 and c equals 3. And there it is, a really nice, clean decomposition. 2 over x plus 1 plus 3 over x squared plus 1. Yeah, it looks complicated at first, but when you just follow the rules, the process is perfectly logical. Okay, for our final and most advanced example, we're going to mix everything together. We've got a simple linear factor, x, combined with a repeated linear factor, x minus 1 squared. This is where all of our skills really have to come together. The setup for this one needs 3 fractions, one for x minus 1, and one for x minus 1 squared. Now, what's really efficient here is using 2 different strategic values. Setting x equals 0 instantly gives us a equals 1, and setting x equals 1 instantly gives us c equals 6. To find that last constant b, we just compare the x squared coefficients, and boom, we find b equals 2. It's a really beautiful mix of techniques.
And here's our complete solution. This whole process just systematically takes a really messy expression and breaks it down into these simpler pieces that are so much easier to work with, especially when you get to calculus.
So now that you've seen how to do it right, let's talk about how it can go wrong. Because honestly, understanding the common mistakes is just as important as knowing the rules in the first place.
Let's just ask the question directly. What are the traps that people fall into most often when they're tackling these kinds of advanced problems? Because, being aware of them is half the battle. Here are the top 3 culprits. First, with a repeated factor like x minus 1 squared, people often forget the first power term, the a over x minus 1. You gotta have both. Second, with quadratic factors, the classic mistake is just putting a constant a on top instead of the required ax plus b. And finally, sometimes you can't get all the answers just by plugging in numbers. You have to remember to also compare coefficients to finish the job.
So you might be wondering, why are we even learning this? Is this just some abstract math exercise? And the answer is no, not at all. This technique has a serious real-world payoff, particularly in engineering. Yeah, this isn't just theory. Engineers are using this exact process all the time to do something called inverting Laplace transforms. And that is absolutely essential for solving the equations that model electrical circuits and control systems. The math we just practiced is fundamental to designing the tech that's all around us.
Take a look at this expression. It's called a transfer function. It might describe a simple circuit or maybe a mechanical system. To figure out how that system actually behaves over time, an engineer has to decompose it using the exact rule for repeated factors that we just learned. This process directly translates that math formula into a real-world prediction. And that pretty much brings us to the end. You have officially leveled up your math skills today. You came in knowing how to handle the simple cases, and now you have the tools to systematically break down fractions with both repeated factors and irreducible quadratics. That's a huge step. So, I'll leave you with this question to think about. Now that you have this really powerful technique in your toolkit, how might it change the way you approach complex problems, not just in this course, but in calculus and any other STEM field you decide to pursue? Thanks for tuning in.